Hello, my name is Aliba Bahit Nurashevna. I'm Associate Professor of International IT University from Kazakhstan, and this is a course, Methods of Nonlinear Programming. Today's topic is Feasible Direction Methods, and I'm using as basis for that slides of Professor Dmitry Bertsekas of MIT, so I hope you will enjoy my lesson today. Today's lecture outline is conditional gradient method and gradient projection methods, and we are considering a feasible direction at n x from set x which is vector is not equal to 0 vector d, such that increment of x plus alpha d is feasible for all sufficiently small positive step size alpha. And note that set of feasible directions at x is the set of all alpha multiplying by distance between z and x, where z the same, obtaining the same set x, and z is not equal x, and for positive step size alpha. I'm considering here like feasible direction, like a practical, achievable, workable, realistic direction. These slides present the feasible direction methods, a general approach in constraint optimization for updating the current point xk while staying within a feasible direction region x. And here is a detailed breakdown. So, feasible direction method, the update rule is xk plus 1 is equal xk plus alpha k dk, where this is a current iterate, a point in the feasible set x. dk, this is a feasible descent direction, satisfying that the gradient transposed gradient of function f xk multiplied by dk is negative, and step size alpha k is positive and such that x k plus 1 is from the same set x. This ensures you are moving downhill. It means reducing the objective f while staying feasible. And a step size is positive, small enough to ensure that xk plus 1 from the same set x. Alternative definition that xk plus 1 is equal xk plus alpha k multiplied by x bar k minus xk, and here x bar k from the same set x is a feasible point that helps define a feasible direction. If xk is not stationary, that it's not a local minimum, then multiplication of transpose gradient of function f in point xk and distance between x bar k and xk is negative. This ensures you're going in a descent direction, and alpha k from the segment from 0 till 1 ensures that the update stays within the feasible region, and it's a convex combination of xk and x bar k. Step size rule, a limited minimization constant alpha k is equal 1, and in this case we choose alpha k to approximately minimize function f over feasible alpha. use a fixed alpha k is equal 1, which may work on simple or well-scaled problems. For Armijo rule, a backtracking line search defined as alpha k is equal beta mk, where beta from the segment 0, 1 and shrinkage factor, for example, like 0.5, and sigma from segment from 0, 1 sufficient decrease parameter, mk, I mean that's mk here, smallest non-negative integer such that the Armijo condition holds, that f xk minus this function from this sum is greater or equal minus sigma beta m multiplied by our multiplication, like transpose gradient and distance between 2 points. This condition ensures that the reduction in function value is significant, proportional to the direction derivative, making the step size both safe and effective. Finalizing, we can formalize a feasible direction method where we move from xk to xk plus 1 along a direction that stays inside of feasible set, decreases the objective, and two ways to define the direction directly as dk, I mean this dk, and directly via x bar k. Step size alpha k is chosen via rules to ensure convergence and feasibility. Here I would like to remind you some definition. For example, a definition of constraint optimization. So we need to minimize some cost function like f of x on some set x from x big. And if we have this constraint on this set, for sure such kind of optimization could be named like constraint. Constraints could include equality constraint or inequality constraints. And in this table you can see the comparison between unconstrained optimization and constraint optimization. For feasible region for constraint optimization, this is subset of Rn defined by constraints. For optimality condition, we can consider Karush-Kuhn-Tucker conditions, which includes gradients of constraints. For unconstrained optimization, gradient just equals 0. For constraint optimization descent direction, only direction that keeps the next point feasible. Stationary points, no feasible descent direction exists. And algorithm use projected gradient, barrier methods, Lagrange multipliers. For complexity, more complex due to constraints and boundary handling. And for example, this constraint could be considered like in this form: x1 plus x2 less or equal 1, or x1 plus x2 squared is equal 1, and so on. And just to remind you, what does mean stationary condition? For stationary condition, stationary point, there is no feasible direction d, such as multiplication of transpose gradient by d is negative, and this usually leads to the Karush-Kuhn-Tucker condition, which generalize that a gradient of cost function f of x is equal 0 to constrained cases. Example of constrained and unconstrained problems. For unconstrained problems, the set of possible points is 0 and gradient is equal 0 as well. For constrained problems, we are minimizing some function which subject to some constraint, which x1 plus x2 is equal 1. And here the set of points is not 0 and a gradient is not 0, but it must be balanced by constraint gradient. For example, like Lagrange multipliers. Let's focus on the convergence theory for the feasible direction methods in constraint optimization. It's established under what conditions the method leads to a stationary point. I mean a point where optimization stops because of no descent direction exists. At first, I can tell about similarity to the unconstrained case. This is referring to the fact that the convergence analysis of constrained feasible direction methods closely resembles that of unconstrained gradient methods, but with the added complexity of maintained feasibility. Gradient-related direction sequence, dk, is gradient related to and the following property can be shown like that. For any subsequence xk from the set of k that converges to the non-stationary point, the corresponding subsequence dk from the same set is bounded and satisfies such kind of condition. I mean, limit of supremum of multiplications, transpose gradient and decay is negative if we consider the same set k big. How can we interpret this? We are considering subsequences of iterates and directions often needed in convergence analysis, and if xk implies to x star and x star is not a stationary point, then the directions dk must still point downhill. So, I mean this multiplication should be negative. Here, the limited supremum of this multiplication is negative. This ensures that there is a uniform descent along the sequence, preventing stagnation away from the optima. This gradient relatedness condition ensures that the method is aligned with the negative gradient, at least asymptotically. Let's consider the proposition about stationary of limit points. This is the main convergence result. Let the sequence xk generated by a feasible direction method, where xk plus 1 is equal xk plus alpha k dk. And dk is gradient related, as explained before. Alpha k is chosen by the limited minimization rule or the Armijo rule, backtracking line search satisfying sufficient decrease condition, and then every limit point of xk is a stationary point. Even if xk doesn't converge to a single point, any accumulation point subsequential limit is a point where no descent direction exists while remaining feasible. So the algorithm won't get stuck away from optimal points. Proof that's nearly identical to the unconstrained case, and this tells us that the proof relies on similar arguments as those in unconstrained gradient methods, like descent property of the algorithm, compactness or boundedness of the iterates, properties of step size, for example, Armijo rule ensures enough decrease, and gradient relatedness ensures convergence towards stationary. The added constraint is need to maintain feasibility, which is why feasible directions and carefully choosing alpha k are important. So, little bit like finalizing, we ensure that the feasible direction method is theoretically sound. If you choose good directions and step sizes, then your iterates won't diverge or cycle, and every limit point will be stationary. That it's a candidate for a constrained local minimum. Being back to my students, I'd like to remind them about stationary and non-stationary points. In optimization, a stationary point is a point where the algorithm can no longer make progress. That there is no feasible direction in which the objective function can decrease or increase if we are finding maximum function, not minimum. And in constraint optimization, a point x star from set Rn is stationary if the gradient vanishes, if gradient is equal 0. This means the function is flat at that point and a local minimum, maximum, or saddle point. I just would like to add that in earlier slides, you can see the definition of gradient-related directions requires that for non-stationary points, the algorithm keeps making descent steps. And the convergence proposition guarantees that every limit point is stationary. That is, the algorithm won't stop prematurely at a point where it could still descend. Here we explain a crucial step in the conditional gradient method. We can name this like Frank-Wolf method, particularly how the direction of movement is chosen at each direct iterations. So update formula looks like that, and here this is the standard update step in the conditional gradient method. You move from xk toward another point x bar k, and step size alpha k from segment 0, 1 controls how far you move in that direction. The direction x bar k minus xk must be a feasible direction. That is, it keeps the iterate inside the constraint set x. So how x bar k is chosen? Its equal argument minimum of this multiplication, again, transpose a gradient vector multiplying by distance between x and xk, and this is a linearization of the original nonlinear objective function. Instead of minimizing the full nonlinear function fx, we minimize its first-order Taylor approximation around xk. Since If f(x_k) is constant with respect to x, we only need to minimize the linear part. And this minimization is done over the feasible set X, which is often a convex polytope in applications like traffic flow, resource allocations, and so on. So xk is a solution to the linearized problem at step k. It gives us a direction that the best improves the linear approximation of f while staying feasible. We assume that X is compact, so X bar K is guaranteed to exist by Weierstrass. We assume that X is compact. This refers to the Weierstrass extreme value theorem, which says a continuous function achieves its minimum and maximum on a compact set. The function of multiplication is linear and thus continuous. Fx set X is compact, closed, and bounded, then the minimum must exist in X. Therefore, X bar K exists and it's well defined. I mean this X bar K. This assumption ensures the well-posedness of the method. So, summarize, X bar K solves a linear subproblem at each step. The update X K plus 1 ensures feasibility. Compactness of X ensures that X bar K always exists due to Weierstrass theorem. And here I just placed some little reminding for my students about the convex polytope. Just definition of this in different cases. A convex polytope is a convex hole over a finite set of points in Rn, or equivalently, a bounded intersection of finitely many half-spaces. In two-dimensional K, it could be a polygon with straight edges, no holes. In three-dimensional K, this is a cube or tetrahedron. And higher dimension, this is harder to visualize, but the same idea applies. It's a multi-dimensional polygon bounded by linear constraint. Now consider the illustration of these two cases. For example, this picture is an illustration of the conditional gradient method, also known as the Frank-Wolf method, used for solving constraint optimization problems of the form minimum of function f x on the set X. So the feasible set X, this is like a gray polygonal region labeled like constraint set X, is a convex polytope, a bounded convex set defined by linear constraints. All movement must stay within the set, and this is our feasible region. Current point X, this is like current iterate. The goal is to move to a better point, that is a point that reduces the objective function f while staying on X. Gradient is direction to the gradient nabla fx. This arrow shows the gradient vector at the point X. Since we are minimizing, the best direction to move would be opposite to the direction. I mean in this direction. And however, we can't necessarily move in that direction directly because of it might leave the feasible region. These concentric curves are level set or contour lines of the objective function fx, and each curve represents points with the same objective value. Moving toward the center means the objective value is decreasing, getting better. Linearization and the direction to x to the x bar. X bar, this is argument minimum of multiplication of transpose gradient vector and distance between z and x. This finds a point and x that minimizes the directional derivative of f at x, and in geometric terms you draw a line in the steepest descent direction, project it onto the boundary of set x, and find the point x bar that gives the most descent. So the vector x bar minus x becomes the search direction. So the next iteration is x k plus 1 is equal x plus alpha multiplying by x bar minus x, where step size alpha from segment 0 to 1. And this means instead of jumping all the way to the x bar, you move partially in this direction, like step by step. So what the picture shows finally, you're at the point x and the convex polytope x. You can't follow minus in opposite direction of gradient directly, so you solve a linear subproblem to find x bar. You move from x toward x bar along a feasible direction, and this movement reduces the objective while staying in x, which is the essence of the conditional gradient method. Let's consider another picture, and this image shows how the conditional gradient method's Frank-Wolf method operates over time and visually explains its characteristic slow sublinear convergence. Here, feasible set x, this is triangle, is the constraint set x, a convex polytope in R2. All iterates in the optimization algorithm must stay within this triangle. These elliptical curves, represent contours, level sets of the objective function f of x. Moving toward the center, labeled x star, decreases the function value. The goal is to reach x star, the minimizer within the feasible set. How we will consider iteration path? The method starts at x0, the initial point. Each update moves along a segment from the current point to some vertex of the triangle. For example, from x0, which lies on the boundary. And this movement corresponds to xk plus 1 is equal xk plus alpha k multiplying by distance between x bar k and xk. Points x1, x2, and so on, x3 get closer to x star, but the path zigzags between the vertices and never moves directly towards the x star. Why is the convergence slow? The figure here illustrates a key weakness of the Frank-Wolf method. Here we can consider zigzag behavior, and the algorithms always moves toward an extreme point, vertex of the feasible set. If the solution lies deep inside the feasible region, like X star, the path to it must be approximate using many short steps between corners. Sublinear convergence rate is known to be fxk minus fx star is equal or minimum from 1 over k, and this is sublinear, meaning the method gets slower over time. The gap shrinks, but more and more iterations are needed to get close to X star. Practical implication. The Frank-Wolf method, conditional gradient method, is simple, projection-free, and works well for large-scale problems or when projection is expensive. But it can be inefficient near the solution, especially if the solution is in the interior of X, as shown here. So, summarize this slide, I can tell the method moves from x0 to x1 to x2 and so on, always staying inside of constraint set X. It follows a path that zigzags between vertices and slowly approaches X star, and this geometric behavior explains its sublinear convergence rate and helps motivate never accelerated variants of the algorithm. Now let's present a convergence proof for the conditional gradient methods, Frank-Wolf method, by showing that the direction sequence is a gradient related, a crucial property required to apply generic convergence theorem. Here, our goal is show direction sequence is gradient related. We want to show the direction sequence dk is equal d x star bar minus xk is gradient related to xk. From the earlier, show the direction sequence dk of the conditional gradient method is gradient related. So the generic convergence result applies. And whereas k is a non-stationary point. The following holds, like limited supremum of multiplication of our two functions is negative. Suppose that xk converges to a non-stationary point x tilde, and then we must prove that xk minus xk tilde that's on k from set k bounded. Subsequence xk converges to a non-stationary point, and now we need to show the first one, that the distance between x bar k and xk is bounded, and second, that limited supremum of this multiplication is negative. So the first relation, a boundedness of direction sequence. We need to show that x bar k minus xk is bounded, and since x bar k and xk from the same set X, and the feasible set X is compact, the difference between any two points in X is bounded, and therefore the direction sequence is bounded. So it's proven. It's proved. And second relation, note that by definition of x bar k, limited of supremum of this multiplication is negative. We prove this using that of definition of xk. X bar k is argument minimum of multiplication, transpose gradient and xk. So for any k from k, and by x implies to infinity, the minimum of right hand side over x from x, and using the non-stationarity of x tilde, we can write such kind of correlation. Take limit superior as k implies to infinity and minimize over all x. We can find of a limited supremum of such kind of correlation, and it would be less or equal minimum, and it should be negative. In this case, x tilde is non-stationary, so minimizing this, we can receive that it would be negative. So it proved. As conclusion, I can tell that both properties needed to show that dk is gradient related are now verified, so dk is bounded, and limited of supremum of such kind of correlation is negative when xk tending to x tilde non-stationary. This allows us to apply the generic convergence theorem, which states if the directions are gradient related and step size are chosen properly, for example using Armijo rule, then every limit point of xk is stationary point. Here we are explaining the gradient projection method, which is a powerful approach for constraint optimization. The key idea is to use gradient information and the project back onto the feasible set to maintain constraint. Purpose: we aim to solve a constraint minimization problem, like a minimum of some function, cost function f of x, and here x from Rn is a convex feasible set. For example, a polytope or ball and so on, and f of x is differentiable. So main iteration formula, the simplest variant of the gradient projection method, is xk plus 1 is equal xk plus alpha k multiplying by x bar k minus xk. Here we can consider like x bar k as a positive part, positive scalar of difference between xk, which is the current point, and sk multiplying by gradient of function f of xk. Sk here as a step length, positive scalar, and this plus here denotes the orthogonal projection onto the feasible set X. Alpha k step size is a relaxation parameter, or step size we can name it, from 0 till 1. So geometric meaning. Step 1. Gradient descent proposal. We can compute an unconstrained gradient descent step xk minus sk multiplied by nabla f of xk. This point may may fall outside the feasible set X. Step 2. Projection. We can project this point back onto this constraint set X. X bar K is equal projection of xk minus sk multiplied by nabla fxk. This gives a point x bar k from x that is as close as possible to the gradient step but lies within the constraint. And move toward the projection, then we can update, either go all the way to x bar alpha k is equal 1, or move part way toward it from alpha k from segment from 0 till 1. So here we can consider that as usual this level curves, contours of equal cost, and gradient steps pointing outside the feasible set, and projection bringing them back inside, and updates move from xk to xk plus 1 staying within x constraint set X. We can see here the several iterations from xk till xk plus 1 to xk plus 2 and back to xk plus 3 and so on. Each follows the patterns in which we can consider each next step like xk plus 1 like positive projection on the set X of distance between xk and sk multiplied by gradient if alpha k step size is equal 1. Depending on the context, alpha k can be chosen as constant, for example 1, or according to the Armijo rule, sufficient decrease condition to guarantee convergence. And line search, limited minimization, we can minimize f xk plus alpha dk over a feasible alpha. And arc-based rule here, when moving along the projection arc, used with variable sk. We can consider special case. For example, if alpha k is identically equal 1, then xk plus 1 identically equal x bar k. And if alpha k is less than 1, then xk plus 1 is in the line segment connecting xk and x bar k. This helps stabilize the iterations and improve convergence near the boundary. We can consider here a step size rule for alpha k. I can summarize this slide as follows. Gradient projection method blends gradually descent with feasibility via projection. Projection helps enforce the constraint xk plus 1. Step size alpha k helps control how far to move forward toward the projection. And visually iterates hug the feasible region, adjusting direction and magnitude. Let's present a convergence proof for the gradient projection method, showing that every limit point of the sequence xk is stationary under certain step size rules like Armijo or a limited minimization. To show that under proper step size selection xk plus 1 is equal xk plus alpha k multiplied by x bar k minus xk, where x bar k is equal positive projection of xk minus sk, nabla f xk, produces iterates xk such that every limit point is stationary. That is, the method converges to an optimal point, or at least no further feasible descent is possible. Assumptions we can have here that the alpha k is chosen via Armijo rule and ensures sufficient decrease, or a limited minimization for xk, which converges to a non-stationary points x tilde. So now we want to prove a contradiction by showing that this cannot happen under the method. So step first is to show gradient relatedness. We need to prove that a norm of x bar k and xk converges to such kind of norm, and such kind of norm is bounded, and limit and supremum of this correlation is less than 0. And this confirms the direction sequence is gradient related, which allows us to apply convergence theorem. So the first relationship is about boundness. We consider such kind of correlation, and it should be bounded because x bar k is positive projection of this one. Of this correlation is always stay in constraint set x, and projection is a non-expansive operation, doesn't increase distances. So x is compact, and the norm, this norm between x bar k and xk convergence, and it's bounded as well. So first condition is satisfied, and the second condition, second relation, is about descent condition. Now we can use a key result from projection theory, and projection of this one, yes. By optimality condition, such kind of projection is less or equal 0 for all x from set x. So choosing that x is equal xk, we get such kind of correlation. And if we will rewrite this, we can consider this less or equal minus 1 over s multiplying by norm of projection squared. Now take the limit and supremum of this limit superior of this correlation. We can see this is a negative, and since x tilde is non-stationary, the projection step is not 0, so the squared norm is strictly positive, and it means so we get strict inequality. So the second condition is satisfied as well. As conclusion, I can tell that since both conditions hold, the direction sequence is gradient related, and we can apply the convergence result. If alpha k is chosen via Armijo or limited minimization, for example, alpha k is equal 1, so every limit point is stationary. Like additional notes, I can tell this if we have constant step size and sk is equal s, assuming that under Lipschitz conditions on gradient f, also holds when using Armijo rules along the projection arc. That is, step size is adjusted as you move toward x bar k. So we formally justify that the gradient projection method, with proper step size strategies, converges to a stationary point. It relies on the first projection optimality conditions, I mean this one projection, and properties of the projection operator. As well, I can tell here that a limiting argument using the non-stationarity assumption. And again, just to remind for my students, Armijo rule and Lipschitz conditions, just to not forget them. Here we will consider a gradient projection method deeper inside, particularly for quadratic functions, and introduces a scaled variant, a Newton-like version. It uses theoretical properties of projection, eigenvalues, and quadratic models to analyze and enhance convergence. So let's consider the quadratic objective functions. That objective is quadratic and Q is positive, I mean matrix Q here positive, symmetric positive definite matrix, so F is convex and smooth. And we can consider like gradient nabla F here like Qx minus B. So constant step size assumptions, like considering like alpha k is identical equal 1, so sk is equal s. This simplifies the update to xk plus 1 and is equal like positive projection of xk minus s nabla f xk. And as always, we can consider this plus here like a projection onto the feasible set X. So convergence analysis via projection properties, we will analyze the norm of this subtraction here, and let's X star the minimizer of F over X. Then we can represent this in following form, and non-expansiveness of projection we consider like for example projection A plus minus projection B is less or equal norm of A minus B. So if we will apply this here, then we can consider this and we can tell that such kind of inequality is valid. And since we have like a gradient of function f considering like qx minus b, where q is a positive matrix and b is vector, and we can get such kind of norm here, like identically matrix minus sq multiplied by xk minus x star. Use a spectral norm of such kind of form like I minus sq, which is governed by the eigenvalues m small and m big, yes, of q. Then we can limit this inequality like less or equal maximum of such kind of correlation. And this gives a contradiction property when S from 0 to over m big, so the method converges linearly under appropriate S. Scaled version, I mean scaled gradient projection, quadratic subproblem. So this is like more advanced update in which we can consider the iteration like xk plus 1, like xk plus alpha k multiplied by x bar k minus xk, where x bar k we can consider like argument of minimum such kind of correlation. And this is quadratic approximation of f at xk using curvature matrix hk, often set as Hessian, and xk is non-stationary. The minimum is negative. That is, you get descent, like multiplication of gradient and distance is negative. We can consider like Newton methods connection if we are set a Hessian in form of squared gradient of cost function f. And we can recover this like a Newton type direction combining second order information with projection. This is more accurate and convergence faster, quadratically near to solution, but this is more expensive. Other variants and extension include projection on expanded constraint set, sometimes loosens constraints to allow larger steps, restricted projection projects only certain coordinates or subsets, and hybrid methods which combine projections with unconstrained subproblem solves, penalty, barrier techniques, and so on. A little bit finalizing the previous slide, I have placed here this table in which feature can have exact description. So again, if we have quadratic objective of cost function in following form, then assumes that matrix Q is positive defined, enables exact gradient and Hessian. Then projection contraction property could be like distance between iterates decreases geometrically under constant step size, governed by eigenvalues of matrix Q. Then step size rule in which we can consider constant S. Then convergence here when step size S satisfies that S is positive but less than 2 over m, big, where m is the largest eigenvalue of matrix Q. And for scaled gradient projection, we can use quadratic subproblem with curvature matrix Hessian for better direction. And then it allows us to give several variations like Newton type method, which sets Hessian like squared gradient. We can receive faster convergence, but computationally more demanding. And the last one, but for sure we can have much more methods like projection variants, includes projecting on expanded restricted sets combining with unconstrained solvers. It was a lesson on feasible direction in framework of course method of nonlinear programming. Here you can see references which I have used for this lesson, including the slides of Professor Dmitry Bertsekas in nonlinear programming and many different sources. Thanks for attention, and again I would like to repeat my name, Bahit Nurashevna Alipova. It was the lesson Feasible Direction in framework of course of International IT University of Kazakhstan. Thanks!